Hello everybody, we are C2 Systems, and today we are presenting a proposal for a carbon capture system via calcium looping for natural gas combined cycling power plants. So now to introduce our team, I am Andrew Forbes.
I'm Ryan Woolery.
I'm Ed Hahn.
And I'm Cheyenne Ernst.
And again, we are C2 Systems. A little bit about our vision for our company. So C2 Systems is supposed to be an engineering design company devoted to developing short to medium term solutions for technologies to help decrease CO2 emissions worldwide in an effort to combat climate change. And so our first project is a carbon capture and sequestration unit with the technology of calcium looping for capturing CO2 from the flue gas from natural gas power plants.
So just to go into some background to contextualize our project, first we'll talk about emissions. As of 2018, global carbon dioxide emissions were up about 3% to 37 billion metric tons per year, and it's projected to continue to rise, as you can see in the figure on the right. Large countries like India and China, as well as many smaller developing nations, are still putting a lot of focus on development of fossil fuel-based energy generation, which is why carbon sequestration and utilization technology development is key for mitigation. As much as we want to focus on development of renewables, we have to look at what's practical, and there's still a lot of carbon dioxide being emitted into our atmosphere, so developing these technologies that will allow us to capture it and effectively remove it from the atmosphere is key. Many countries have developed cap and trade, carbon taxes, or tax incentives, including the United States. Our internal tax code, section 45Q, outlines some performance-based tax incentives for power plants and industrial processes that sequester their carbon rather than releasing it into the atmosphere. And now to move into talking about why specifically we're focusing on natural gas instead of coal. Natural gas plants are gaining popularity throughout the United States. As of last year, about 13 gigawatts of coal were retired and about 15 gigawatts of natural gas replaced it. 60% of the power generation that came through in the United States was natural gas, and 90% of that 60% was combined cycle, which is why we're specifically focusing on combined cycle natural gas power plants. Additionally, natural gas is approaching price equality with coal because we have better technology and larger reserves. Additionally, natural gas inherently burns cleaner than coal. It has a greater hydrogen to carbon ratio, which allows it to have about 45% less carbon dioxide emitted per kilowatt hour by mass. There's also reduced particulate matter and less volatile compounds, and inherently lower sulfur and nitrogen compounds released, making it safer in general.
Now at the same time, enhanced oil recovery has been on the rise, and this is expected to increase the need of CO2. Now this technology uses captured CO2 to extract oil from previously unattainable reservoirs, and this CO2 is not released into the atmosphere. And the market is estimated to reach about $90 billion by 2025 due to the increasing number of aged wells and the rising oil demand. And there are plenty of sites within Middle America and actually throughout the nation.
So let's just talk about calcium looping in general as a technology. So it's a second generation post-combustion carbon capture technology. So what that means is that the carbon dioxide is captured after the fuel has already been burnt and it's already been used to generate electricity. The key reaction is shown right here. The forward reaction is the formation of calcium carbonate, commonly known as limestone. That reaction is exothermic, and for our purposes, we assume that it's fast. Normally, it's actually diffusion limited if you let it go to completion. The reverse reaction is the decomposition of that limestone. This is endothermic, which requires a lot of significant amount of heat to actually make it proceed. Once again, this reaction is also similarly very fast. The equilibrium is very temperature sensitive, so for example, at above 850 degrees Celsius, you almost have exclusively decomposition, so that allows us to actually maintain selectivity of the reaction. In terms of prior art, there actually have been previous like pilot and bench scale plants that have been developed throughout the world. This one right here is for Incarcisc in Spain. It's about 1.7 megawatts. However, the biggest difference here is that most of them actually been based, or almost all of them have been based around either coal or cement manufacturing. There's been no practical demonstration of this technology on natural gas. And calcium looping is actually already being used by a company up in Canada called Carbon Engineering. They use this actually for direct air capture. So basically taking carbon dioxide directly from the air and turning it into liquid fuel.
Now for our business plan. So C2 Systems is a design company with a pilot plant that's focused on experimentation and showcasing. And for our pilot plant, we will be owning and operating the system, and we'll keep the revenues, but we'll give a portion of the tax credits that we receive to the adjacent power plant. And while we're operating as contractors, the full-scale calcium looping process will be designed by C2 Systems, and we'll charge a fee for engineering and the supply chain setup based on the scope of the project. But ultimately, the power plants will own the equipment and reap the benefits of the revenues. For funding, initially we want to work for EPA and Department of Energy grants as well as private investment. And some carbon or capture costs are subsidized by the 45Q tax credits. And these subsidize both carbon dioxide used for enhanced oil recovery as well as carbon dioxide stored safely underground. And part of our monetization is we can sell off some of the byproducts from this process, including lime, which can be sold to cement manufacturers, and the captured CO2, which can be sold to enhance oil recovery. So for phase one, we want to work on our bench scale model, and this is demonstrating proof of concept and gathering more funding. And then we'll move on to the pilot plant, which will partner with a natural gas power plant and take 1 to 5 megawatts worth of their flue gas and capture the CO2 from that. And we'll work on networking and experimentation. And then phase 3 will be targeting and pitching our process to power plants and actually working as a design company. And we're going to target plants in the Texas and Midwest region.
Yep.
And the reason why we chose these two areas was because of the high natural gas power plant density, the amount of limestone resources within the areas, the amount of cement manufacturing within these regions, as well as both sites have a large potential for enhanced oil recovery reservoirs. So we chose a pilot plant location, a small-sized Black Hawk power plant, which is a 225 megawatt capacity. There's ample surrounding real estate for construction. It's in between San Antonio and Houston, which is perfect for attracting potential clients. And the area is home to many enhanced oil recovery sites as well as cement manufacturers. Now, taking a look at some of our competitors, our main one is amine scrubbing. It's commercially available and it's proven, and the Fluor Corporation is one of these. It works in a similar vein as us as a design company, as well as Petronova coal plant, which is one of the biggest carbon capture systems out there, and it's in the same region as us in the Houston area, utilizing enhanced oil recovery. And there's also direct air capture, which removes existing CO2 from air, and Carbon Engineering has taken the lead on this, taking the air capture and moving it to liquid fuel. And all these companies, I have to note, they're all located within North America. Now, what makes our process different? We have a reduced theoretical energy penalty of 4 to 6% compared to amine scrubbing, which is around 8 to 12%. And this is tied to heat recovery and sorbent regeneration. And low temperatures in amine scrubbing restrict heat recovery options. We also have a reduced capital and operating costs. Limestone is cheap and widely available. We also have relatively simple process equipment. It's very similar to cement manufacturing. And we can use existing carbon capture gas and steam generators. And investors have taken notice. The market growth is very promising, with carbon capture market projected to grow at 16% continual annual growth rate through 2024. Next slide.
So now I'm going to walk you through our process design. So our initial design was pretty simple. We started with two reactors in a looping series. They were both fluidized bed reactors. We have direct fuel feed to the calciner in order to minimize efficiency losses on that end, and we implemented cyclones at the end of each reactor to actually separate out the dust and gas from bulk solids. So why do we actually choose fluidized beds, though? Inherently, they're inherently not very mechanically complex. It can best be summed up as a very tall and thin tube. However, what this allows us to get is a very strong gas and solids mixing to maximize the surface area contact and make sure that the reaction proceeds as quickly as possible. And we also implemented oxy-fuel combustion in the calciner. What this actually allows us to do is it reduces the harmful byproducts called nitrogen oxides, which can act as lung irritants and are long-term and have long-term toxicity. And it actually allows us to run at a higher temperature while using actually even less fuel. So that gives us an additional process efficiency advantage. However, as we were going through this, we actually ran into several design challenges. The first one is that the flue gas from a natural gas combined cycle plant is actually very lean in terms of carbon dioxide content. It's about 4 to 5% versus about 14% by volume in a coal plant. So this is actually a really big design problem. What this actually means is that we had to carbonate at lower temperatures, and what this ultimately means is that the required mix of preheating streams actually decreases the process efficiency. The sorbent also actually degrades as it actually loops through the system. As you may have seen, actually, when you saw the reaction before, it actually works pretty similarly to a catalytic reaction. The calcium carbonate actually gets regenerated over multiple cycles. However, just like normal catalysts, the activity actually does decrease. So about over 5 to 7 duty cycles, the conversion and the capture efficiency decreases from about 70% to 20%. That's very significant. Carbonation is also inherently diffusion limited. Basically, there's a fast surface reaction, and then the carbon dioxide has to diffuse into the calcium oxide to actually reach the inner contents, and that's to get it to go to completion. And finally, it can all really be summed up into massive efficiency losses due to very hot heat streams that in the initial design weren't actually being managed. So now we have our process flow. We kept the dual circulating fluidized beds. They're about 15 meters tall and about 0.75 meters in diameter. Once again, this is a pilot plant. We integrated a heat cycle recovery loop using supercritical steam. We recovered heat from the gas streams using heat recovery steam generators. We use heat exchangers on solid streams to basically preheat or extract heat. Once again, the carbonator. The carbonation reaction is actually exothermic, so we actually have to manage the temperature in that one to avoid a thermal runaway that actually turns it into a calciner. So that's actually also recovered using hot steam. We recycle a portion of the rich carbon dioxide to the carbonator to actually increase the feed amount of carbon dioxide, which allows us to actually carbonate at a higher temperature. This actually increases our energy efficiency. And finally, we actually added a recarboner at the end of the carbonator, which basically uses a very rich stream of carbon dioxide to actually further regenerate the activity of the sorbent, and that increases our duty lifespan by about 50%. So to basically add further complexity to this, the heat recovery cycle can be described by is basically supercritical steam loop that involves three turbines: high pressure, intermediate pressure, and low pressure. The intermediate pressure turbine was added after our simulation work, where we found that we could actually extract even more work out of the system. The control scheme that we implemented provides comprehensive temperature flow and pressure control. We use PLCs to actually to give us intelligent temperature control over multiple systems at one time from one point. The valve fail, in the event of a system failure, the entire process is actually designed to shut down, and the flue gas will actually just simply bypass the system. There's no reaction anymore. This actually allows us to avoid an over-pressurization and over-temperature problems. All control valves, in this case, because we want gas to actually flow out of the system, are normally open. And manual bypass valves are actually present inside the loop in order to make sure that in the event of a catastrophic system failure, the system can also still be safely purged by an operator. So taking a look at our primary unit operations, we have, like I said before, we have 4 of them. We have the calciner, carbonator, recarbonator, and turbines. All these operate at very high, significantly high temperatures, anywhere from 650 degrees to about 900 degrees Celsius. The pressures in the main reactor is actually relatively mild, but because we're working with supercritical steam, the steam can reach pressures of upwards of 270 bar. In terms of general hazards, the main ones are right there. It's high temperature, high oxygen content in the calciner, which poses an ignition risk. There are fine corrosive particles everywhere. We did a hazard analysis, or HAZOP and FMEA. So the main hazards actually come from calcium oxide and calcium carbonate. These are fine dust particles. Calcium oxide has long-term acute toxicity effects. So it has both acute toxicity and chronic toxicity effects in terms of long-term exposure. So gas masks or dust masks and goggles and other PPE such as that have to be worn at all times when actually working around the system. There's a mild exposure risk to carbon dioxide and carbon monoxide as well. However, the system is inherently sealed to actually prevent this. We don't want any leaks. So naturally, the system will actually vent out of about one of the two, either a rich or lean gas stream. And once again, as Cheyenne actually mentioned earlier, natural gas inherently contains a very low amounts of nitrogen and sulfur, so the risks from nitrogen oxides and sulfur oxides are actually relatively low. And once again, we are managing high temperatures and pressures, so the appropriate PPE such as insulated suits, gloves, and everything like that has to be worn at all times when working in the proximity. These two tables right here basically sum up the general hazards with them. Once again, we're dealing with some corrosive species, and some of them are actually toxic, but we've placed measures in place to make sure the exposure risk is low.
Can I just ask a question here?
Sure.
The carbon monoxide, you put it in the category of oxidizer.
Yes, actually. For a lot of available MSDSs, it's actually indicated as an oxidizer. When we reviewed it, when at very high temperatures, it could actually ignite.
It can ignite?
Yeah.
At high temperature?
Yeah.
Okay, but it's also highly toxic?
Yeah, it's also extremely toxic. It's acutely toxic at relatively low concentrations.
Yeah. I think that's more dangerous than being chemical.
Yeah.
All right, now to go over our process simulation in Aspen. So this is our flow sheet. This looks pretty similar to the PNID that Ed showed. So we basically have our main solids looping in the dark black, along with our steam loop in the pink. So just talk about a little bit about the decisions that we made in our simulation. For the reactors, we chose to use our stoic reactors with just a extended reaction that was determined from empirical data. This was after having a conversation with a professor at an English university who is a expert in calcium looping. He basically told us that for the purpose of simulation, it was fine to just use these simplified models because the reactions are pretty quick. Additionally, for heat exchangers, which are very important for our heat recovery system, instead of using normal heat exchanger blocks that have two streams going in, two streams going out, we chose to use the double heater method. So we just had a pair of heater blocks connected by a heat stream. This is because we basically had temperature looping over, which couldn't happen in real life. So the hot stream would end up being colder than the cold stream at the end. So we chose to use two different heaters for each heat exchanger. Additionally, for the calciner heating, instead of actually using a combustion method in Aspen, we just chose to use a heating duty. This was just a simplification. Last thing was that flue gas impurities were a big issue because they would make side reactions. We called up a plant manager at the Merrimack coal plant in New Hampshire, and he basically told us that most power plants do have unit processes to take out impurities before the flue gas actually gets released. So for our results for our 1 megawatt pilot scale, we ended up being able to capture 93% of the CO2 in the flue gas stream. This is on par with other carbon capture technologies, which usually want to be about 90% or higher total carbon capture. So what this amounts to is about 834 cars worth of CO2 being removed per year. And this is with a 2 to 3% continuous solids purge of the calcium oxide. In terms of the energy, for our pilot scale, we assumed an isentropic efficiency of 0.86, which is a little bit high for our turbines. Additionally, one thing to note is that we had a higher energy penalty for natural gas plants because the efficiency is higher. So if you use fuel to heat our reactors, you're basically losing out on more energy that could be used to make electricity. And so with all that, we got a simulated net energy penalty of 7.3%. This is comparable to other simulations in literature, which are calcium looping with natural gas plants. We did use one generous assumption, and so we think the reason why our number isn't lower is because of some heat recovery loop inefficiencies that are difficult to model in Aspen effectively. We also modeled a full-scale 250 megawatts equivalent flue gas plant. So effectively what we did is we just multiplied inlet flow rates by 250, resolved all the issues that came after that. What we ended up getting was about 90% CO2 capture rate, which again is in line with literature. We got an energy penalty of 6.9%, and additionally about 212,000 cars worth of CO2 is removed from the road. That's about 1 million metric tons per year. This is about on proportion with the Petronova carbon capture plant. And this energy penalty is actually lower than a lot of the values that we find for mean scrubbing in literature. These are usually around 9 to 10% for the same sort of setup, which is a simulation with natural gas plants.
So let's just break down our process economics. So for our economic analysis, we relied on the Aspen Plus Economic Analyzer, APEA, to actually provide us estimates for both our pilot plant and our 250 megawatt full-scale plant. We incurred significant equipment costs, about just over $4 million, including installation, was actually attributed counts towards our capital cost. This is actually expected to fall as we actually scale up due to economies of scale. And the adjusted cost that we actually describe right here counts basically before the start of basic engineering. This allows us to account for basically everything that goes in before you actually pay someone to actually design the plant. The costs are actually the cost is around $11.2 million. This is actually relatively high, but we expect this to be high. For a pilot plant, once again, economies of scale don't work in our favor. But we did some research and we actually validated that our pilot plant estimates are actually in line with other pilot plant estimates. Typically they're in the 1 to 10 $1 million range, depending on the process that you're actually using. Farmer plants tend to be more expensive. So just to do a breakdown of our capital cost, once again, it's $11.2 million in total. 24% of that is attributed directly to the cost of purchasing the equipment, the most expensive of which are actually the compressors and turbines. This is just owed to the large volume of gas that they actually had to go process through. Between the two reactors, the most expensive one is the carbonator. While the carbonator and the calciner are from a physical size perspective pretty much identical, the carbonator actually needs to be jacketed so that we can actually implement our heat recovery loop. So that actually adds about 30% more cost. Other fees such as rent and other installation fees are actually accounted for in here. Once again, Aspen doesn't actually distinguish. Aspen doesn't actually indicate exactly which part of the wiring fee is part of installation, which part is just part of like OSBL. So taking a look at our operating costs, we have operating costs of about $2.4 million per year. Once again, there are significant contributions from labor and overhead. These are actually expected to basically scale favorably, so their contributions are expected to actually go down as the plant scale goes up. There should be more costs associated with plant overhead, such as rent, maintenance, and other fees, as the plant capacity actually scales up, and we'll see that in a moment. The utilities are actually $234,000 per year. This is actually within typical estimates. Most of this is actually from high temperature steam. However, it should be noted that since we use the double heater method in Aspen, this actually adds additional utilities that don't actually normally appear. For example, a double heater can actually model a heat recovery steam generator, which doesn't actually have like additional steam streams instead of just the two streams that normally actually come in. This actually totally amounts to a capture cost of $619 per metric ton of carbon dioxide captured. This is actually very high. Nominally, it needs to be in the $25 to $40 range, but this all ties back into economies of scale. We expect this number to actually be high, and we evaluate this a little just based on capital costs alone. If we actually operating costs alone. If we factored capital costs in this and took it over 20 years, the number is actually closer to 720. Once again, not in our favor, but our full-scale analysis was better. So taking a look at our process revenues, the process actually generates about $216,000 of revenue in 1 year. This is due to calcium oxide and carbon dioxide. You can sell these at about $120 and $35 per metric ton respectively. Now assuming that we can actually sell all of it, that gets us to our value right over there. This actually decreases our net removal cost down to $563 per metric ton, but ultimately due to our high operating costs, the plant inherently has no net profit. In terms of design revenues, just taking a look at the capital cost breakdown, the design and engineering portion was about $1.7 million. This is the portion in our phase 3 plan that the C2 systems would actually collect. After taxes and fees, this would go down to about $1.2 million, but that would be the business's actual intake. So we ran a full-scale analysis on the 250 megawatt plant. And one of the issues that we actually had was that we hit Aspen's sizing limits on some of the process equipment such as turbines. An interesting case was that the low-pressure turbine would run at 65 megawatts generating capacity, and Aspen can only size it up to 1.5 megawatts. So you don't want to have 44 turbines. So we had to estimate some of the costs by hand. So these can be considered more order of magnitude estimates. The capital cost is around $290 million. All main unit ops cost between $25 to $65 million each. We had an operating cost of about $87 million per year based on Aspen estimates. This is because of extremely high heating and fuel costs. You can see by that pie chart right over there. 68% of it's actually attributed literally just to heating costs. This is actually probably closer to $55 million per year for an actual operating plant, which is that $55 million is based on just operating costs for a 250 megawatt power plant in general. But when we factor in our revenues, which are actually considerable in this case, the net cost of operation go down to about $33 million per year. So what this actually means is that we have multiple figures for net removal cost. If we ignore capital costs, we capture at about $89 per metric ton. However, when we factor in capital expenses, operating expenses, and take it over 20 years, that can actually go down to either $104 per metric ton, taking the high number, or $48 per metric ton if we actually take it with including revenues. So this is actually within the nominal range that we're looking at. This low value this value is better than what mean scrubbing can actually provide right now, and is projected to go down as calcium looping adoption actually grows and we approach like nth of a kind design costs. So those would go down by maybe additional 20%.
Now the truth is carbon tax legislation we feel like is on the rise globally. Bipartisan legislation in the US actually introduced would create a carbon tax, raising it to $115 per metric ton by 2032 by increases of $10 per metric ton a year. And a majority of the 2020 candidates expressed support for the net zero greenhouse gas emissions in 10 years. And in order to compete with solar and wind, fossil fuel power plants need to adapt with carbon capture or they will not be able to keep up. And calcium looping is projected to be the cheaper and more efficient option and is the best chance at avoiding profit loss from future carbon taxes, especially when you consider further implementations of the technology. And we assume it will become viable once tax credit and carbon tax reaches greater than $48 per metric ton, and it currently is at $35 per metric ton.
So just to kind of move into a summary and conclude here, our main findings. So our first kind of initial thing is going to be making a pilot plant as proof of concept. That's going to be located at the Blackhawk Power Plant in Borger, Texas. After we do that and we prove our concept and sort of have that up and running, we're going to move into operating as an LLC that does design, contracting, and supply chain management with existing natural gas combined cycle power plants. We're going to be targeting Texas and the Midwest because of the existing infrastructure that they have there with their proximity to limestone quarries and enhanced oil recovery sites. Our calcium looping process specifically utilizes heat recovery to increase our process efficiency, giving us a competitive edge. Additionally, calcium looping in general is more economically competitive and better process technology than the current amine scrubbing. Our high cost is expected for the pilot plant, as Ed mentioned. However, economies of scale are going to work in our favor, and as we scale up and operate with larger power plants, our costs will go down a lot. And then just to kind of touch on our simulation results one more time, at the pilot scale, we were able to effectively remove 834 cars from the road in terms of carbon dioxide sequestered, and at full-scale operation, we expect to be able to remove over 200,000 cars from the road in terms of the carbon dioxide that we will be able to sequester. And then just high level, adopting calcium looping for carbon capture and sequestration is absolutely essential for natural gas power plants in general to avoid profit loss in the future as these tax credits continue to rise. So for recommendations in future development, we recommend that plants implement enhanced gas recirculation prior to the calcium looping process as it increases efficiency and offsets some of that energy penalty. And we also plan to lobby for federal and state increase in tax incentives and increases in tax credits as well. Because as Ryan mentioned, once we see that happening, that'll make us our process economically beneficial as well as environmentally beneficial.
Any questions?
Sure. I have two actually. One is a kind of technical and one economic question.
Sure.
The technical one is this plant is producing a lot of CO2.
Mm-hmm.
It's basically you're taking a dilute stream of CO2 and you're producing concentrated or pure CO2.
Yep.
What's the physical form of the CO2, and did you consider how you're going to get that to potential customers?
So basically the process, because you get such a concentrated stream, you can actually basically concentrate down into a liquid form, and these pipelines actually already exist. There's a lot of existing CCS infrastructure in Texas specifically because those plants actually operate there. So you can concentrate it down into a liquid form, and you can either transfer it by tanker or by pipeline.
Good. The other question I had is if we look at it's getting to the economics, and you may have answered it, but I'd like to maybe clarify. If you look at the full-scale plant, you've got, and let's assume you can get it built, so forget the capital cost. If you look at the operating cost of that, it seems that from your analysis, selling the CO2 is not enough to cover the operating costs. So then you've got the whole question about tax incentives, carbon tax. And my question is, if you assume you forget about the capital costs, if you look at the operating costs, are the tax incentives currently available anywhere large enough to meet the gap between your operating costs and your sell product?
Yes, actually. So one thing is that, for example, in Denmark and the EU, they've actually implemented, in certain countries in the EU, because they operate, ultimately they operate independently, have implemented pretty stringent carbon taxes. Denmark, for example, imposes about a €60 fine per metric ton of carbon dioxide. So there are certain locales which this can actually definitely work in. In the US, we have to admit right now it's not as viable. $35 isn't actually enough to offset that $48 cost. But as you might have actually seen, as we scaled up, this is a 250 megawatt operation, right? And you can actually see that the process revenue is actually significantly increased as relative to the operating cost, right? So as we expect to see that as we scale to, for example, 500, which is closer to more typical plant scale, that that the revenue cost can actually eclipse that operating cost. So that way you can actually generate revenue out of this. Once again, the scaling ultimately appears to work in our favor. Yeah.
So I saw for the Capstone, you're working at 900 degrees C at 15 bar. It's a lot of materials that can handle that. Like, what have you guys looked at what you would need to build it out of, and then did you incorporate that new material into your economics evaluation?
Yeah. So actually, just a correction on that, it operates at around 5 bar. The biggest thing is that steel actually, most grades of steel actually can withstand up to well above 1,000 degrees, but for long-term usage, then they might not be as useful. We calculated it out as about 316L stainless steel, which can operate at continuous at around up to about 1,100 degrees for like continuous operation without significant wear. So those are actually factored into our calculations when we sized everything.
Let me see if I get this right. So you're capturing CO2 using this classic European, you're sending CO2 liquid. So what are the users, what kind of users do you see downstream?
Oh, users?
Yeah.
Mostly petroleum industry, I guess, for the enhanced oil recovery sites. Oh, what do you mean by the users?
So what are you going to do with the CO2? You have collected all the CO2, what are you going to do with it?
Oh yeah, we're gonna use it with the enhanced oil recovery. So we're gonna inject it into the ground or sell it to a company that would be able to do that. And they're able to extract actually a lot more oil that way than traditional methods.
Also,
Currently they use water, frac.
Yeah, and actually this is like a lot more efficient. It's been proven to be a lot more efficient.
What else besides?
Another potential source is to sell it to cement manufacturers who can like pump it into the cement and then it's effectively stored like infinitely.
Also, like soft drinks too. A lot of they need it for carbonation. I believe there's some other industries as well.
Yeah, right now a lot of the carbon dioxide, interesting enough, that gets used in industry actually gets mined. So by actually being able to take this out of power plants and purifying it, you can actually prevent them from mining more of it. So instead of taking more stuff out of the ground, in that case, it's already out, it's been generated, so you're just selling to them. Another interesting one is...
So the carbon dioxide you say is currently mined, CO2?
Yeah, a lot of carbon dioxide is interestingly enough mined from the ground. There actually are underground reservoirs in many states in the U.S. that actually supply a lot of the supply. Also, another one is, we mentioned Carbon Engineering Limited, right? So they use a gas to fuel process. So they turn the captured carbon dioxide that they have and they run it through a reverse water-gas shift and followed by a Fischer-Tropsch process to actually generate liquid hydrocarbon fuel out of it. That's like kind of similar to gasoline, right? So as this technology actually develops, that demand for carbon dioxide goes up as you can actually turn it into even more fuel instead of this pretty inert stuff that's not really useful in most contexts.
Though there's still some challenges with the conversion of CO2 to methane or liquid fuels.
Yeah, right now a lot of it's in like the cost efficiency of like hydrogen, for example, but as that technology proceeds along, that cost has been steadily going down. So eventually the cost of producing like liquid fuel from that kind of stuff could potentially be profitable.
And so you see this power plant or your process to be as a standalone process, or is it going to be paired with factories or companies that produce or that generate CO2?
It would be built on the site of power plants. So effectively, the way that our system is set up, it's just 2 giant towers. So it doesn't take up a lot of like area in terms of the actual plant. So it should just be built on there. I know that the power plant manager that I was talking to, he said that usually at most power plants they have solids handling systems themselves. So the limestone supply can be integrated into that. So it'd just be directly on site at power plants.
So this is like for coal power plants, or?
That one was a coal power plant, yes. For natural gas, might be a little bit more difficult to implement the solids handling. But I'm assuming that if they can do it at coal, then they can do it at natural gas too. It just may be a little bit more money to set up. Yeah.
How often do you have to like swap out your limestone catalysts?
So once it reaches steady state, once again, it's actually continuous purge, about 2 to 3% by mass. So once again, because it's a continuous process, it doesn't actually swap out by batch process. So it's just continuous.
Yeah. So what we had was we basically have like fresh limestone going directly into the calciner where it gets converted into calcium oxide, and then as the calcium oxide goes to the carbonator, 2 to 3% of that is just let out. So that purged.
Right. Makes sense.
So if we go back to the catalyst,
Yep.
you said something about the yield that drops after
5 to 7 duty cycles, yeah.
And what was your solution for that again?
So the solution is actually recarbonate. So if you actually expose calcium oxide and calcium carbonate to very high purity calcium carbon dioxide, it can actually restore some of that functionality. That's partially, it's like reactivation of sites of pores and stuff like that. And it increases it pretty significantly. There's a paper that, we said 5 to 7 duty cycles, it could drop down to about 70%, right? In studies, it's actually been shown that up to 20 duty cycles, the efficiency loss was only maybe like 10 to 20% with recarbonation. So it has a very significant effect.
Did you consider other types of catalysts, or?
I mean, you can definitely do other kinds of carbonates because the reaction mechanism would be similar.
Well, no, in terms of capturing the CO2. So, for example, metal organic frameworks, or.
We did actually consider those for a while. We know there's actually another Capstone group that did that. However, the thing is, metal organic frameworks right now, you can't make them in mass. They're very expensive. They're inherently very expensive to produce. And while they definitely last longer than calcium carbonate, they're just nowhere near as cheap. So for a practical solution right now, calcium looping is where you want to go.
Any other questions?
All right.
Awesome. Thank you very
Thank you
much.
guys.